Classical Physics Tutoring, Chapter 7, Section 1, General Theory of Relativity. Now, we are moving on to the general theory from the special theory. Okay, so what's the difference? The difference is we handle acceleration effect. Okay, so when we talk about acceleration, the problem is the Newton didn't question this, but he was this question was nagging him, but Einstein clarified it. So you have a mass, and gravity used the mass, the gravity equation, right? Gravity constant. This mass, and you have a mass. When you calculate acceleration, right, as a same mass. Why? Okay, so we assume we're talking about same mass, and Newton's law said, well, the material has a mass, and the mass has a gravity, and the mass has an acceleration based on this equation. Newton said that, so we accept it. Okay, but in deep inside, is this really correct? So what Einstein did is try to unite these two things. Okay, the mass that causes gravity and the mass that causes acceleration, they're completely the same thing. So using potential equation, the F, you remember that we did field theory, divergent F is going to be, this is the density of the mass, right? Okay, now we also have this, and if it's gravity, it's going to be like that. Okay, so essentially the acceleration caused by gravity is has a mass. It's acting, the mass is used for both acceleration and gravity, and they are same mass. And by the Einstein tried to show that by choosing correct unit, kilograms, they can be exactly same. Okay, that's called the principle of equivalency. And why he needed to do that? Well, in the general theory of relativity, what is different is, okay, we had Earth and satellite orbiting around, right? And this satellite has a gravity, but if you are in a satellite, you cannot see outside. You don't feel gravity because centrifugal force acting on it. Okay, and the way we dealt before is frame. This is a frame 1, and this is frame 2. Frame 1 look at the satellite and said, hey, you have a gravity, right? And we are pulling you to fall. But the falling, this gravity is just changing the direction. So instead of falling directly, since you have a speed v, it's fall this way, and fall this way. So it's constantly falling by gravity, and that's what circular motion is. But frame 2 said, no, I don't have any gravity because centrifugal force canceling it. And this is acceleration, right? And this is gravity. So the zero gravity. And only way you can reconcile this is not the relative relationship. When we had a special theory, A and B is moving at the speed v. Well, for A, B is moving, but for B is moving. But for B, A is moving. In this case, away, moving away. They have equal observation, right? And this is the foundation of special theory of relativity. You cannot say who is right. They have exactly the same observation, and we had the Lorentz transformation equation to deal with each claim. But when you have gravity or acceleration, the situation is different. So this is B. B said no gravity, no acceleration. And A said, yeah, there is a gravity, and you are moving according to the gravity. Okay, so the gravity things and acceleration things act on frame. So you have a frame 1 and the frame 2. Frame 2 get acceleration, and the frame 1 don't see it. This is independent. So it's not really relative in a sense. Okay? So how do you deal with it? Another nagging question is, what is this centrifugal force? Is that a real force? It's a fake force. But for frame B, in this case 2, it's real force to cancel out the gravity. That's why he got zero gravity there. Okay, so how do you deal with this kind of situation? Now, as I said, if it's speed, inertial speed, you cannot tell who is moving. But there is acceleration, you can tell. For example, you have a train going, and the platform, man is standing, and the boy inside has a baseball. Okay, and when it's moving v, okay, the boy thinks he is moving at speed v. Man standing on the platform thinks boy is moving, and that's impossible to say who is moving. But when the train is accelerating, the situation is different. What's happened is, when boy toss a ball, it's come back here, not the same place, right? So boy said inside the train, I know I'm accelerating. He doesn't have to look at the other guy, right? The guy, a man standing on the platform, he's irrelevant for this situation, because boy knows already, toss the ball, it's come back here, accelerating. If ball come back here, deaccelerating. So acceleration is happen regardless the other frame. So it's independent. Acceleration act on this. And also gravity is the same way. Gravity act on this independent. You feel the gravity. You can tell you are in confined room and you hold a ball. Ball drop this way. You know gravity is acting on this, regardless the situation on the other frame. Okay? So, and we just say this mass, acceleration and the gravity is equivalent. So what's happened is the Einstein's job is to reconcile how to do that. Now he made potential field, the space is skewed by the potential field like this. Okay, so what happened is, if this create a gravity field like this, and gravity field created by satellite, and this is Earth, this kind of slope, right? It's like slope, right? But suddenly gravity field dip because of the satellite weight. Okay, now the way he reconciliate is, okay, the gravity is created by both this curved space and force is generated to the direction of minimum path to come down the slope in a curve. Okay, so the gravity act this way. Okay, so this guy stay in his own gravity well. This guy, the gravity has a slope. If there's no gravity on this one, then it start falling. But if there is a gravity, so what happened is this one create its own and stay there. So you don't need the fictitious force of centrifugal force or anything. The gravity is replaced by curved space, and the curved space calls the acceleration force. Okay, and that's all you need. This is united theory of gravity and acceleration. So he nicely made this model. The gravity alone can explain why this guy is zero gravity here, because the way the space is curved, it's sitting here comfortably and doesn't move. Okay, so basically that's what Einstein did in General Theory of Relativity. Okay, now when he created this model and explained the relevance of frame 1 and frame 2, the strange things happen, because this is not just curved space, that's time also included in the equation. Remember, Lorentz transformation has time in it, the time dilated, right? So his Einstein's equation for this gravity curved space show that gravity which is the curved space, this area, the time dilate, again time dilation. Now this time dilation is different from special theory of relativity, that time dilation is in the Lorentz transformation, but this is additional time dilation by gravity. So after he made a model to explain all the nagging question in Newton's mechanics using curved space, the curved space is curved in such a way by gravity and time. Okay, this time dilations came up. Okay, so he estimated using that his equation, and this is the result. R is far distance away from the gravity center. If you have a gravity center, it's curved like that. R, T0 is time taking speed at the gravity center, T0, and Ts is frame 2 observing. Or T2. So T0 is ticking much slower than T2 observer. Okay, so this is not a relative. Actually, whoever in the gravity field, time tick slower, right? So all kind of speculation is possible. Say this is Earth, you fly to the other planet which is very heavy, and you stay there a few years and come back. So what's happened? You're much younger than people on the Earth. Okay, that's another way to do time traveling. You find a very strong gravity planet and stay there a few years and come back. Then you didn't gain age as fast as people on Earth. So there are many ways to do time traveling. So this is additional time dilation happens by the curved space. Okay, because this curved space equation includes a t, and you compare the t here and here, then the ticking rate is different. Okay, that's the first thing he found after he accomplished uniting this, the acceleration and gravity. Now second things he discovered is when you have, say, sun, very heavy. This is the sun. Drawings here. The light pass, because if you make a contour map of the curved space, it's become like that. The lights come here, and lights is gonna bend according to this curved space and go out. Okay, and this is gonna be the focus point. So if you put the eye here, you can see something behind the star bigger. And if you have a star here, the famous experiment, Einstein predicted the star behind the sun, say it's here in this direction. Normally you cannot see, the sun is in the way, but you can actually see this. The reason you don't see it is because the sun's light is so shiny. So the few group travel to the spot of sun's eclipse. Sun is totally covered. See if this star see it. Okay, so the star's position was as if here instead of real position, because the light's bent this way. And how much it's bent is the equation here. Okay, so what's happened is they calculate this, and they calculated this and the gravity, sun's gravity, and it's pretty much as predicted by this theory. And Einstein got famous, certainly. It's all the newspaper reported Einstein's prediction. This one was confirmed by sun eclipse. They observed the star position, and that was this much off. Okay, that means light bent around the sun by gravity. So that's a bending light. So Einstein theory for uniting gravity and acceleration brought time dilation and the bending light and some other effect explained in the astronomy. Okay, and the curved space now is in the next video we will show you more conclusion from the general theory of relativity, and it's mostly astronomy and cosmology, and it's nothing to do with the engineering work you're going to learn if you're engineering major, but physics majors, those are the interest of the topics. So I hope you enjoyed this video, and if you like, subscribe.